So, welcome to the last lecture on the module on VLSI testing, which is on high level fault modeling and RTL level testing. So, basically if you look at the previous series of lectures, so we were discussing on different type of optimization techniques like high level fault models, then how basically one type of high level fault model can actually go for coverage of stacked fault model. Then we also have discussed very interesting theory on how we can compress these test patterns, and then inside the circuit we can again decompress it so that the test volume remains smaller. And then also we have seen some kind of design for optimization techniques for design for testability, like how the hardware on the chips which are required for testing can be reduced, like some kind of scan chain based optimization, etc. But if you look at all the things, basically we are emphasizing on gate level design, that we know that structural fault model, structural testing with a fault model is one of the de facto standard, because nobody could handle the complexity of functional testing. So, but everywhere the concept was till date that we are going for a structural test with a fault model, and everything was boiling down to a gate level. So, now why gate level? Because till the advent of some kind of very sophisticated circuits like NOCs and SOCs, more or less we could handle VLSI circuits testing and design, etc., with quite a good level of optimization and timing requirements, or you can say about the cost required to implement the algorithms, time required to generate the test patterns, time required to do the verification were quite reasonable at the gate level. But when these NOCs and SOCs have come into picture, or even the gate level with structural fault model has started blowing up. So, today's lectures will be basically concentrating on the directions what people are thinking, that how we have to move away from gate level, all analysis from gate level modeling to some level of abstraction like register transfer level. So, the motivation before these NOCs and SOCs type of sophisticated designs, where we were looking mainly at the gate level. Now, why at the gate level? Because gate level basically has a good correlation with so called the transistor level and the basic device level. And when you talk about structure, basically we do not think about the functionality of the circuit. And structure means basically if you tell me what is the structure of a digital circuit, we will all tell that it is basically gates and interconnects. And when you, if somebody tells about what is the structure of an analog circuit, you will tell about transistors. So, for us basically the basic atomic level for digital design were gates. So, if you and statistically it was also verified that if you can handle the fault models at the gate level, you can have a very good correlation with the defects at the transistor or the silicon level. So, that is why we were all thinking in terms of the gate level design, gate level testing, gate level verification, etc. But when this number actually moved to NOCs and SOCs, gate level, the number of gates and interconnects became so high that not even the structural test with most advanced optimization techniques could give test pattern generation in a reasonable amount of time. So, we had to go away from this lower level to higher level abstraction, and in fact this is one optimization basically which leads to slightly quality of compromise in the quality of test patterns. But nothing we can do, because if we start going for gate level based testing in NOCs and SOCs, the amount of test time generation will be in years and months basically, which will give a very infeasible way of solving the problem. So, to address it, address the high level of complexity, we have to trade off slight level of quality of service to achieve a reasonable timing. So, today's lecture plan is to give you an abstract idea of how people are now moving from gate level to a newer abstraction level. This is actually a paradigm shift, and this has been started in last 5 to 6 years. The major emphasis has been going from the gate level to more abstraction level. So, let us go about it. So, till now what was the de facto standard? That we have to go with structural test and fault models. And what is a fault model? Fault model basically abstracts out the real defects. That is one option, that is one idea, and the second idea, it should be very much correlated with the absolute defect level. Like you cannot have a very abstract fault model which has no correlation with the defect level. The idea is, I am repeating many times, but that is one thing which is to go into everybody's mind, that a fault model should simplify testing, but at the same time it should have a good correlation with the defect level, so that you actually the quality of test solution is maintained. But now, if you look at the complexity of structural test from the view of the VLSI circuits, which is slightly less complex than the NOCs and SOCs. So, if you go for stacked fault model, which is the de facto standard used everywhere, so we know that generally it is twice the number of nets, because there can be a stacked 0 and stacked 1. So, and in fact there is a lot of concepts like fault collapsing, one pattern can detect multiple patterns. So, actually the number of faults actually comes down than the twice the number of nets, it is much lower than that. But what is the problem? That is actually the backtracking. So what happens, already we have discussed that if you sensitize the fault, then you have to propagate the value to the output and then you have to also justify it. So by doing it, many times you find out that one net should be 0 because for propagation and for justification it needs to be 1. So there is a conflict. So conflicts has to be resolved and you have to keep on doing it till as many paths from the fault site are possible to propagate the value to the output, till either the fault is successfully propagated, sensitized, propagated and justified, or you find out that there is no more path available to do it. So the backtracking is the main complexity here. So if you think of a very big circuit, the number of nets will also be high, the number of gates will also be high. Of course, the number of faults is not of a big concern. This you have to remember, because due to fault collapsing by equivalence, dominance, like an AND gate, if you take an AND gate, a stack at 0 fault at the output and a stack at 0 fault at the input are equivalent. Because always you require a 1 and a 1 to 1 as the input to test it. But the problem is because of backtrack. The more larger circuits you have more larger the number of fan outs will be, and more number of options you will have to send the values of the fault effect to the output, and similarly for the justification of the lines. So more number of choices, more number of different values you can put in the signals, and more number of conflicts can arise. And this has to be done till you get a successful drive to the successful fault propagation and justification. So backtracking is the major problem, and if you think of a very big circuit, it actually kills the timing requirements to go for the automatic test pattern generation. So that backtracking is a big problem apart from the number of faults. Secondly, we are looking at the bridging fault model. So bridging fault model, again the number of faults are slightly larger because we take combination of 2. So number of nets into 2, any 2 pair can be having a bridging fault. But anyway, we try to minimize it or optimize it by making slightly smaller size windows where lines are more congested and where where the designer tells that there can be good chances of having bridging faults, so you can do that. So the number of faults are slightly larger. Again, there is a backtracking issue, because already we have seen in the last classes that bridging fault is similar to testing of a stacked fault, but say for one line you go for stacked fault testing, but some other line which two are coupled, you have a constraint that whether when you test a stacked 0 fault over here, maybe this line you have to make 1 or something like that. Already we have seen different type of bridging fault model like an AND gate fault model and an OR gate bridging fault model. So the idea there we have seen that one line of the bridging fault has to be tested for stacked 0 and stacked 1. At the same time, you should also have a constraint at the other line which is involved in coupling. So more constraints you put, more conflicts you will have, and additional backtrack will be required. So this control as the dominating point. So one point is getting dominated where you are going for test the stacked 0 and stacked 1 fault, but the other line which is dominating it has to be put to a constraint. Like as I told you, in this case maybe you was checking for stacked 0, here you have to keep a 1. So more number of such control points you have, more complexity the stuff has because of the backtrack. So the main issues are all happening in such cases because of the backtrack issue. So if you have a very big circuit, lot of choices, and the complexity becomes exponentially prohibitive, because looking at all paths is an exponential problem. Even with the heuristics to find out which is a good path for propagating the fault effect, etc., still for a very big circuit like an NOC and SOC, such type of algorithms are prohibitively complex, and you do not get the test patterns in a reasonable amount of time. Also we have seen, sorry, this is about the at speed test model, so pardon, it is at speed or delay fault, is about the delay fault. So in delay fault actually, basically this is the delay fault. So in fact the delay fault basically is very similar to the stacked fault complexity, because you have to just verify the, in one line you have to find out whether it rises properly or it falls properly. So there is no more additional constraint, but the only issue is that you have to apply at speed, the value has to be applied at speed. So it does not involve any kind of computational complexity as such, only thing is that you should have a higher value, higher speed ATE, or sometimes you have to put the signals inside the built-in self-test mode on chip circuit which will apply. So that complexity you have already seen how it can be handled by DFT circuit. So till now, so what we have gathered is the major problem of ATPG happens because of backtracking. And backtrack, and of course the secondary factor is the number of faults, because if the number of nets increase. But the idea here is that if the circuit becomes very large, the backtracking is becoming so complex that we have to deviate away from this and we have to go for some kind of abstraction. So then what actually came is nowadays called abstraction. So you cannot go to very low level like a gate or transistor, you have to move away from it. So one of the most important issues of testing in deep submicron or very large NOCs and SOCs is scalability. This is because all the test schemes till last 20 to 30 years were all concentrating on gate levels and they were trying to optimize it. which actually makes the problem exponential. Because if you think that I have two numbers to add, so they are 32-bit numbers, I have two adders, so maybe the complexity is around something of order of 32. But then I make the numbers as 64-bit, then eventually the complexity becomes enormously high. Then if you can have a more higher precision numbers and the number maybe say 128 bits. So the data path, actually the data width keeps on becoming increasing in nature because of the precision, etc., and the complexity of testing becomes very high. But if we go think of some kind of abstraction that we will consider these two 32-bit numbers or 64-bit numbers as a single number, then a plus b or a minus b you have to test, then whether it is a 64-bit number, whether it is a 32-bit number, or whether it is 1028-bit number does not matter. So this is one level of abstraction. But where we are compromising, we are not going for bit level testing. And already statistics over the years have verified that if you are going for gate level testing, that is a bit level testing with fault model, then the accuracy or correlation is very, very high. But we do not know but exactly what is the correlation or how high it is if you are going for such kind of abstraction. That is, instead of considering A and B as bit level numbers, we are considering A and B as a whole number together, and we are not going into the depth of the bit level. So that nobody knows, but still that is the only way to solve the problem, because jumping from 4-bit to 8-bit, 8-bit to 32-bit, and from 128-bit such numbers, the problem of testing the adder will become so complex even in the structural level that the ATPG solution will not be possible within a logical amount of time. This is only about an adder, but think of a circuit with n number of IP cores where all the 128 processors are running in a single core, then you can think that adder is only a very small part of the design. So it can be hundreds of orders of 100 times the adders or 200 times the size of the adder, that complex circuits are there. So there is no other option than to go for higher levels of abstraction. So that is why people try to model the whole test problem in a very high level of abstraction called register transfer level or something called the architectural level. So you all know about register transfer level, that we have blocks like adders, multipliers, subtractors, multiplexers, registers, instead of having flip-flops and gates. And of course, if you are modeling at such a high level of the circuit, of course your test fault model also should be at a very higher level of abstraction. Like the stacked fault model was very much consistent or was moving in hand with the gate level, because we are saying that the input and the output of the gates should not have a stacked 0 or stacked 1. But such concept is very difficult to apply at the higher level of abstraction. So not only the model is abstracted, circuit model is abstracted, also you have to have fault models which are also at the same level of abstraction, so that there is a good hand-to-hand correlation. So before going into all the algorithms, we will start with an example. This is a GCD computation, which is a very well known theory which we learn in high school. So what we do, basically we take two numbers, say in1 and in2, and we find out the GCD. So what we do, the well known algorithm is that till V1 is equal to V2, we compare V1 and V2, and then we say V1 is equal to V2 minus V1. If V2 is larger, else we do the reverse, and we keep on doing it till the numbers are equal, and then whatever is when they become equal, the GCD actually happens is stored in the output of V1. We already know that this is a very simple algorithm, like say we are taking say 10 and 5. So first step we will subtract 10 and 5, so it will be 5, and so this is say V2 and this is V1. So we will subtract 10 from 5, and then actually V2 will be equal to 5, then V2 is equal to V1 in the next step. So the GCD is 10 of 5, about 5 and 10 is 5 itself. Very well known high school mathematics. So this is the actually algorithm. Say that we want to implement a circuit out of it. So if you look at the gate level, it is going to have around say 1000 kind of a gates to implement a circuit, because you require a subtractor, you require a comparator, and everything will depend on what is the size of the numbers in. So if you consider a 32-bit numbers, the size may be around 100, maybe around 1000 gates. But if you consider in1 and in2 as 128-bit numbers, the size will be extremely high in number of gates. So that will make it very complex to find out the ATPG solutions because of this huge size of the circuit. But if you look at the RTL level, it is totally immaterial what is the size of the inputs of size of N1 and N2. It looks as a smaller and nice problem. So all these things can be possible if you are modeling at this level of abstraction, that at the block level, which is called the register transfer level. So I am showing you the basic whole RTL diagram for the circuit. Now we will go to see how it works basically, and we are going to zoom the individual part of it. So let me just show one part which is required to do the computation, which is first part is computing basically NEQ, that is whether V1 is equal to V2 and one part is the comparator. I am just showing you because just you keep it in mind, because that thing will not be required too much in discussion, because for every iteration this is a combinational circuit. You will just calculate whether V1 is not equal to V2 and another block will compare which is greater. But again you have to appreciate the size of these two blocks will heavily depend on the bit width of the numbers input and input 2. But in this case, as we have very much abstracted, it is an RTL design, we have abstracted V1 and V2 as a single number. So actually if you look at, this is actually the data path. So all circuits have a data path and a control path. So data path will actually talk about how the numbers are moving, what are the arithmetic operations happening, and the control path, as you know, will control that which part of the multiplexer has to go in, whether it will be V1 minus V2 or V2 minus V1, how the multiplexing has to be set. So that the controller will do. So the controller is always generally a small finite state machine which is smaller in size, generally compared to an RTL design path. So if the bit width of the numbers increase, like in1 is 32 bit to 128 bit, the size of the data path will be enormously large in terms of the gates. But the controller will always be the same, because controller takes the number like V1 is V2, V1 not equal to V2, that is the output of these combinational blocks it will take and give the appropriate signals to control the multiplexers. So basically even in very large circuits or very very complex circuits, we are more concerned with the testing of the optimization for testing of the data path. Controller more or less remains similar if you are taking a single bit number or a 128 bit number. So I am not saying that it is very simple to test the data path, control path rather, but actually with the increase in the complexity of circuits, the data path problem becomes much higher or more involved in the number of gates compared to the controller path. So basically we will, in this work and most other works, people always try to optimize the data path mainly. But again in this work we will show you both. So let us try to look at the first part. So basically what happens, okay, sorry, let me just concentrate on this. So there is one multiplexer, a marks 3 and one multiplexer is marks 4. So what we do, this signal which is called select 3 4, this is some signal, the controller will give the value. So it will be first made 0, so that the in1 goes to marks 3 and in2 goes to marks 4. Then you make the second line, if you see, select 1 also, this is select 1 will be equal to 1 and select 2 will also will be equal to 1. So in this case what I have told you, that select 3 4 is equal to 0, so that the in1 and in2 will be going to the respective markses. Then this select 1 and select 2 will be equal to it will be equal to 1, so that this value, that is in1, will reaches. So just as you look, so what I was saying, that 32 we are making it select 34 equal to 0, seal 1 and seal 2 marks values we are making it to 1, so that input will go via this and will be registered, will be locked into the register. That means now we are reading the value of in1 and in2 in two registers, that is reg A and reg B. Again notifying, it's very important to understand that when you are talking about the register transfer level modeling, the reg 1 and reg 2 are not single flip flops, they are actually the register bank. That means if A and in1 and in2 are 32 bit numbers, then the register A and register B will be 32 bits, or they will have 32 bit registers. But if it is 128 bit, reg A and reg B will have 128 and 128 bit, 128 different flip flops to latch the values. So but here we are modeling it as a single block. That is the beauty of abstraction in the register transfer level. Now what we are losing here, we will be losing the bit level granularity of the test. We will be testing register A as a whole, we will be testing register B as a whole, but we may not be able to test at the very granular level, that the bit level of all the flip flops involved in the register A and B. But again the complexity is coming down from 128 bit to 1 bit. But again this backtracking problem is an exponential problem. Order is exponential because you have multiple number of paths from one node to the another node, and all path combinations is exponential in the number of nets, and which is obviously very proportional to the number of gates. So if you reduce the number of flip flops or gates from 128 to 1, obviously complexity drastically comes down exponentially. So that is why the RTL level actually models everything in terms of blocks, so that they can hugely bring down the complexity level in the, drastically the level is brought down, so that the ATPG etc. becomes very very simple. But here actually, as I told you, there is slight compromise in quality because we cannot test at the granular level. And all the statistics, a good correlation between stacked faults at gate level, real defects exist for the gate level. But for the RTL level, which is a very new concept, people are still struggling to find out what is the complexity, what is the correlation. Obviously complexity is very low, but what is the correlation with real defects? People have found out it is not bad, it is quite good in fact, but still it is currently under study, and statistical data is still being studied and gathered to find out very good quality RTL fault models. Anyway, coming back to our discussion. So in the first step, basically as we have seen, the in1 and in2 will be latched at the two registers, which is nothing basically, this in1 and in2 will be registered at V1 and V2. So register 1 actually has V1 and register actually has V2. So this step is done. So this is standard algorithm, but I am just going to give you an highlight so that you understand what is basically register transfer model. Then what we do? Then as I told you, once these values V1 and V2 are latched, this NEQ and less than equal to, these two values will be fed to the controller. So if V1 is not equal to V2, then the loop has to go, but if basically this becomes equal, then the data will be latched from register RA. So whenever this one is equal to 0, that means they are not equal to become 0, that means they are equal. In that case, the output guy who is going to take the output, he will capture the value from register 1. That is the end of iteration. But anyway, before that, let us assume that the LT becomes 1. That means V2 is greater than V1. So if V2 is greater than V1, then what should happen basically? If V2 is greater than V1, then we should have the operation called V2 minus V1. So if we should have the operation called V2 minus V1. We are assuming that this less than equal to is 1. So basically that is V1 is less than V2, this value is equal to 1, that means V2 is greater than V1. So this operation should happen. So how this operation would happen? So the controller will get the value of 1 less than equal to 1. So that means it knows that V2 is greater than V1. So you have to arrange the multiplexers in such a manner that it happens basically. So you can see this is a subtractor which will take the value from marks 5 and it will subtract the value from marks 6. So the controller will make 5, 6 equal to 1. The value of this control will be equal to 1. So let us see what happens basically. So if it happens, then basically here 1 means the V2 will be coming, the V2 will be coming out from this guy to here, and also this one is connected, so is also equal to 1. So V1 will be connected from here to here. Here it is V1. So in the subtractor you will have the value of V2 minus V1. If I make 5, 6 equal to 1. Now who will make it? The controller will make it. How the controller will decide? It will decide because the LT value is equal to 1. This block is saying that this is the case. Now what? Now again V2 minus V1 will be latched to register 2. Because V2 minus V1 will be registered to V1, because if you look at the algorithm, so V2 minus V1 will be latched to V2. So now again I am coming back. So now again the multiplexer arrangement will be something like, so this part I should not do anything basically. So select will be equal to, select 1 will be equal to 0 and this one will be actually equal to 1. Now let us see, and of course this value will be equal to 1. Now let us see how it happens. So if you look at, so now this one is having the value of V2 minus V1, select 4 equal to 1 I have made equal to 1. So basically in fact from both these transistors, both these multiplexers 3 and 4, I am sending the value of V2 minus V1. Now basically output of marks 3 and marks 4 both is now having the value of V2 minus V1. So now you see register A, that is equal to V1, should remain constant. Now why it should remain constant? Because I am doing V2 minus V1. So V1 should retain. So I am making the select 1 equal to 0. Controller will make it because LT is equal to 1. So in that case select 1 will be equal to 0. So old value of V2 and V1 will be fed back, which is constrained. So V1 will remain as it is. But in this case if I make select equal to 1, the marks 4 output will go. Marks 4 is having the value of subtracted output, which is V2 minus V1. So V2 will now have the value of V2 minus V1. So basically this one will be coming over here. You are going to have the value of V2 minus V1, and here the old value of V1 will be there and it will be restrained and it will have the old value. Similarly, whenever the value of 0, it will be 0 in the other case. So in this case just the reverse thing is going to happen. In this case basically you should have the So in this case you will have the value of 0. So in this case basically it will be V1 minus V2. Okay, this one will be have to be made 1. So basically V1 minus V2 will be flowing to both these parts. In this case just the reverse has to be done. Select should be 0. So if it is 0, the old value of V2 will be fed over here. But in this case select 1 will be equal to made 1. So in this case the value of V1 minus V2 will be fed over here. So this way the multiplexing arrangement is possible and it actually works in this manner. So this is very easy, and basically now one more thing I have to say, the two emphasis thing is that one, as you have seen, this is the data path. So what is the data path? Data path actually takes care of the fact that how the V1 and V2 are moving. What is the controller doing? The controller, based on the value of V1 and V2 subtraction greater than less than, is setting the value of the multiplexers so that the exact operations are happening and the data is flowing in the correct path in the data. And again, the complexity highly increases in all circuits, because if the number bits are increasing, the data path size blows up. But controller will more or less remain the same. As you can easily appreciate that even if I have a A1, V1 and V2 as 4-bit numbers, or they are about 1028-bit numbers, the controller will remain same, only the size of this data path will become enormously large. So we always target to test the data path in a very abstract manner. So in this case, as you can easily appreciate that even if the V1 and V2 becomes 128-bit numbers, the size of this circuit in these terms will remain the same. So when you are testing circuit at this level of abstraction, we have how many blocks? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So only 11 blocks are there, or you can say that 11 RTL blocks are there. So they are synonymous to gates in the gate level testing. So only a circuit with 11 gates are there, I have to test it. It is very simple. But if I have a 128-bit numbers in this data path, the number of gates will be around tens of thousands. So you can find out what is the complexity and how it will be difficult to generate the test patterns at that depth in the gate level. Now you will also appreciate the fact that this RTL model for this GCD, you will be only as very 0.0001% of the original circuit in an NOC and SOC, because in NOC and SOC are hundreds and thousands of IP cores, hundreds of IP cores in a single die, and in which case the arithmetic part of this course will have hundreds and thousands of circuits whose size will be equivalent to the GCD. So very difficult problem in that way. So we go for this abstract level testing. So I am not going to discuss about this controller path. So basically it is the control path. So just I can tell you in gist what happens. Basically whatever control signals I told you is generated is shown over here. Like for example, if I am the start state of the controller, then reset is equal to 1, there is some reset signal, and basically select 1 equal to 1 and select 2 equal to 1. That means what? These two guys are equal to 1, so that the values and cell 4 also equal to 1. These two are 1 and select 4 equal to 0. So select 4 equal to 0 means the E in values will be latched over here. So basically this is the controller structure. Then automatically you go to the next state. In the next state basically you again do some kind of computation, and at many cases you can see that always I am looking for the less than signal. Sometimes it will depend whether the less than signal is 0 or 1, whether it will go to state Q3 and Q4. In state Q3 you may do V2 minus V1, and in state Q4 you will do V1 minus V2. So whatever I have told you, the control signals which will be generated are represented by this finite state machine of the GCD algorithm. That means all the explanation I have done, how the signals are generated etc. is depicted in this table and the text below. So you can just have a reading through this, which will make your idea very clear. So these are the entire explanation of the steps. So there will be actually 4 states. So 4 state means it will be 2-bit machine. So basically the number of flip flops will be 2. 4 state means 5 states Q0 to Q4. So number of flip flops required will be 3 to implement the circuit. So now again, important part is this very standard digital design. You can easily go back to your higher BTech level digital design, and you can easily find out how a state machine can be implemented. But again, re-emphasizing the fact that the control path is very simple in terms of number of gates compared to the data path. Data path, as I told you, will blow up with the number of size of the input bit width. But you can see the controller will remain same, and the controller size is how much? Very, very small, because only 5 state. 5 state means 3 flip flops, and number of gates to represent this finite state machine will be not more than any 10, or maximum the number of gates will be 10 or 20, not more than that. If you make a combinational circuit using your standard digital design fundamentals, you will find out the size will not be more than 3 flip flops and around 10 to 20 gates. So testing of the control path at the abstraction level is possible, but not a real emphasis at this level. Really people are facing problem with this data path. So we will be mainly concentrating on the data path in this case. And also one more assumption we have, that all these registers, that is the flip flops, and also the flip flops will be used to represent these states, are also scan enabled. That is obviously possible, very easily possible. Now as I told you, you can very easily appreciate that what I will do with the stacked fault over here. You can say that I can only have stacked fault on the inputs and outputs. You can do that, but people have found out statistically that that is a very devastating fault model. No correlation can be found, not even 20% correlation could be found if you directly apply a stacked fault model over here. It is not that people have not tried. People have found out that stacked fault model is well accepted. I have a very abstract model. Let us try to put some stacked faults in this place and try to see what happens. So that means you are considering this whole line together, whole V1 together. That means either the number is in 1 or the number is 0. But basically, say for example, I am taking a 3-bit number. So let me say 001. So these are number. So in a stacked fault model, In the gate level, you will see whether this line is stuck at 0, 1, this line is stuck at 0, 1, this line is stuck at 0. But in the RTL level, this whole number is considered as a single number. So either the number is 0, 0, 0, 0, 0, 1 itself, that is the original number, or it will be all zeros or all ones, because the whole number is taken together as stuck at 0 and stuck at 1. So, it do not have the individual granularity. So, if you do it, statistically it is found that stacked fault model at the RTL is a very bad fault model because the correlation is very, very low. So, you have to go something beyond that. So, people started thinking about high level fault models for RTL, and again I have to tell that this is not a very old concept. So, still statistical data is being collected, people are trying to find out which is a good fault model, which is slightly complicated, but still you can fix with the RTL and still the defect correlation is very good. So, as we all know, fault model is a convenient representation of physical defects or failures to the operation of the circuit. Here the circuit is at the RTL level and physical level is a transistor. There is a lot of gap in the levels from a transistor level to a basically RTL level. Initially it was very good, the RTL level, it was the gate level and the transistor level, there was a 1/2 correlation, but now the half of correlation has increased very high. So, therefore, the correlation make from a transistor level to RTL level is very difficult. And we always know that a fault model is good because if there is good correlation between the physical defects and the fault model. Now, how people have started thinking about it. So, people know that transistor level fault models are very good fault models because transistor level fault models are very correlated to the defect level. Now, the next reliable fault level is gate level, that is the stacked fault level. Transistor level anyway we could not go, but that is the best possible fault model you can say is the device level fault model. But anyway, I mean beyond physics, it is the, if you go slightly more abstract from that, then the transistor level fault model will be very good because there will be 1/2 correlated with the defects. Again that is more very complex, so we all accepted the stacked 0, stacked 1 fault model, which was at the gate level. Now the gate level is directly correlated with transistors. So therefore people have found good correlation. Now people have started finding out that we should find out fault models at the RTL level, we should have a very good correlation with the gate level, because we cannot have a correlation between RTL level and transistor level. It will be very difficult to find out and mathematically show or statistically find out. Rather, people have tried to find out such fault models which have good correlation with the gate level and the RTL level, and they are thinking of an indirect transitive relation. That is, from the gate level, very good correlation with the transistor level, and if we make good fault models which have very good correlation with the gate level, maybe there should be a good correlation with the transistor level and defect level. So that is the idea of the high level fault models which is applicable for RTL. Now we are going to see some of the fault models which are being proposed for the RTL level, but still, as I told you, this is a very new area which are still trying to find out good fault models with a very good correlation. This is under study basically. So these are the fault models which should be at a very high level of abstraction, and the design of fault models should be very much coherent with the constructs of the RTL, as the faults will be indexed in the RTL file. That is, you should not have kind of a gate level or transistor level business when you are talking about RTL level model and testing. This should be very similar to the faults which can be embedded in the RTL. So RTL, as you see, are very much similar to something kind of a software. So these are software basically, nothing but it's a C code or a code. I can very easily translate it to a C code. So people have tried to get motivated from the fault models from the software engineering errors, because it's a huge subject in software engineering is software testing. So what type of fault models they take? People have tried to adopt those models into the RTL model, because RTL is nothing but a code. Then people are trying to find out how the correlation can happen at the real gate level and the transistor level. That is the idea of research when you are thinking about testing of very complex circuits and the fault model at those levels. So different fault models, input stacked, output stacked. So in fact they are, again I am emphasizing that is the whole input taken together. So all the bits will be 0 or all the input bits will be 1. We cannot have any intermediate chains in between. If then stack, else if stack, assignment failure, dead clause failure, and so many fault models are there. I will discuss most important of them once, but again they are all motivated very much from the software engineering perspective, that is from the code, because RTL itself is a code in that manner. So input stacked fault. So I have a very simple code which says that primary inputs x and y, output is out 1, then it says that if logic expression something, then out equal to x, this one. Now x and y may be 128 bit numbers, but then what is a stacked 0 fault? You will say that out equal to 0 and this equal to 0. That means x and y, all the inputs are basically stacked 0. Importantly, all the whole x, if it is 128 bit numbers, all the 128 inputs will be 0 and all the 128 bit inputs will be 1 in the two different cases. So instead of having 2 to the power 128 different combinations, or if I should not call it 2 to the power 128, in fact 2 into 128, because each bit will be either 0 or 1. So 2 into 128 is now converted to only 2. So a huge number drop is there. So basically if you are taking a gate level model, so all the bits has to be individually considered 0 1 0 1 like that. But in this case I am clubbing all the bits together and it is either all zeros and all ones. So there is a compromise here, because already it was proved that if you are taking each individual bit of this 128 x and y numbers, then very good correlation happens with the transistor level. But now you are just taking two numbers, all zeros and all ones. So among this 128, 2 into 128 stacked faults, I am just taking 2, all zeros and all ones. How much correlated they are? So people have found that the correlation is not bad, maybe around 70 to 80%, but not as high as 99.9%. But still people say that at the huge high level of this design complexity of NOCs and SOCs, we cannot go for 128 bit level. So but this is only one fault model. That is, we have to apply all these and even many more, so to get around 90 to 95% more coverage complexity or coverage or correlation level. So they may be, this one is going to give you some 30% correlation. Then we have if stacked fault. It means what? This is a logic expression which says that if some expression, then A equal to in 1, else if A equal to in 2. Some code is there. Then basically what is the if stack? That means this one will be stuck at 1. That is always A will be equal to in 1, because always the if condition will be true. I can also have if stuck at 0. That means always the if clause will be false. These are all the fault models which are taken from basically software engineering perspective, and this we can very easily fit to all the RTL. This actually corresponds to if then else means a multiplexer. This fault model will directly fit to a multiplexer. This one will directly fit to assignment values, so forth. So all these models has to be taken together to go for RTL testing, then the correlation will be acceptable level. But again the numbers will be very, very less compared to the gate level, because always we are considering this in and in 1 and in 2 irrespective of their bit size. And there is something called assignment failure. So we are saying that is a code, in this case light equal to green, but all the inputs may be stuck to yellow. Then whatever condition you give, everywhere the assignment will be yellow. So this is some kind of a constant assignment failure. So this is another fault model. So in that way n number of different fault models exist, which I am not going to cover elaborately in this. They are all mainly coming from the software engineering perspective. So some 20 to 30 different fault models people have proposed, mainly from the software engineering, like if stuck, else stuck, some case condition is there, some case condition is stuck, assignment is stuck, etc. and so forth. Dead clause, that means dead code, etc., etc., etc. So all these if you take together, then you may get an acceptable level of coverage, but not by the individual models. Individual models, the coverage, or I mean what do I say, correlation is extremely low. But always they are having a good level of abstraction, and the complexity actually comes down heavily down, considering the fact that the circuits are very large, then there is no other option to go for this abstraction. In case of high level fault model like RTL or behavioral, there does not exist any close relation with defect levels in the circuits. So they are not considered as reliable fault models. So one fault model is not very reliable. So you have to take lots of fault models together, test it, and then only we have found out statistically the reliability is quite high, but not as much as the gate level stacked bridging and delay fault. But still we have no other choice but to go in this research direction. Since last 4 to 5 years, as I was telling you, all the test engineers have started moving in this direction, because we are left with no other solution than finding out more and more accurate RTL fault models and go at the higher level of abstraction. But as I told you, but it is verified that there exists good correlation between high level fault model and the gate level models. Gate level models again have good correlation with physical level. So there is an indirect jump. So people are actually believing or trying to find out that we have to test at the RTL level what are the good fault models at the RTL level. So now again I'll come back to the GCD example, take a real fault, do an ATPG, and then tell you the procedure. So here I am taking an example of a if then else fault. So this is an if then else statement. Then one fault is that it is a swapping condition. So output 1, if some condition is true, else input 2. In this case it is just reversed. So instead of the input 1, the position is 2. If some condition holds, the output will be input 2, and else the output is input 1, but now they are flipped. This is constant output, that whatever may be the condition, input 1 will go, and the other condition is whatever may be the condition, the input 2 will go to the output. So basically they are the 4 fault models which are very much appropriate for a multiplexer. So people have found out that if you test for all these faults in a multiplexer, the correlation is very, very high with a gate level model. So what we do, one is the swapping, and one is the constant input, and one is the constant output. That is, one A will always go, other B will always go, and the other is there will be a swapping. That are the 3 fault models basically, and one is the normal basically. So I should not call it actually 4, basically 3. One is actually the normal condition. So 3 faults will be considered over here, and in this circuit if you take, which is the equivalent gate level for the mux, so there are actually 9 lines over here. So 9 into 2 will be 18 stacked faults. So from 18 I have come down to 9. But now you think that if A and B are 128 bit numbers, so in this case still the number of faults will be 3, but in this case it will be 9 into 128 into 2. So with the rise in the data bit, the testing of the RTL data path becomes simpler, while at the gate level it actually blows up like anything. So therefore, to make the data path complex, testing complexity simple, people have to or must go for RTL or some abstract level of testing. There is no other solution in the current time, because nowadays our bit precisions are also high, the bits of the numbers are increasing in width. So therefore, that is the only way. So this example actually directly shows an example that from 3 faults basically we are coming down to from 18 faults we are coming down to 3 faults if the mux is a single bit multiplexer. It will, the gap will rise when the bit width will increase. So now basically this is the RTL, same RTL circuit we are thinking. Now I am going to take you to the example how to go for a test. We are assuming that the mux 2 this mux 5 has a fault. Let me zoom over here so it will be easier for you. So this has a fault. So now what is the fault? I am taking the swap fault. So that means what? If in this case if select 5 is equal to 0, so V1 will go to the output. If this one is equal to 1, V2 will go to the output. But now because of the fault, what is going to happen? There is a swap. That means if select is equal to 1 basically, here we are going to have the answer as V1, and if select is equal to 0, the output will be V2. So just the reverse. Just look at it, what will be the effect of the fault. So I rub it off and say I say that select is equal to 0. So if select is equal to 0, V2 will be coming out of mux 6, because again still we are always going for the assumption that single fault model. Nobody has been able to go for 2 or more higher level fault models, because that will make the complexity of NC2, NC3 and will blow up. Till now nobody is trying in this direction, or a very few group is trying to find out what is the advantage and disadvantage, but as far as I know people are finding more disadvantages compared to advantages if you are taking 2 faults at a time, 3 faults at a time. Anyway, so 0 of this means the V1 will come as the output. Here what is going to happen? Here V2 means V1 should come, but because of the fault there is a crisscross, and this is going to come as the output, which will be again V2. So the answer will be V2 minus V2, which will be actually equal to 0. Right, that is the effect of the fault. Now again if I take the other side, if I take, remove everything, and if I take mux is equal to 1. So if I take the mux 5, 6 equal to 1, V1 will be coming at the output. Here equal to 1, that means basically V2 should come out, but it will not. V1 is going to come out basically, and because of this swap, and again it will be V1 minus V2, sorry V1 minus V1, because 1, here is the flop, is the reverse, so this is going to come out V1 minus V1, the answer is 0. So you can highly easily appreciate that because of this fault, this crisscross fault, let me erase it, and this is basically a criss fault. So what is going to happen? I am going to have the answer here V1 minus V2, V1 minus V1, or V2 minus V2, instead of V1 minus V2 or V2 minus V1. So that is the problem that is going to happen. So that is actually the fault over here. So I have to go again for the same business, sensitize, propagate and justify, same philosophy will apply. Let us see how it happens. Let me zoom it for you. So this is where is the case. So I have to sensitize. So how I will sensitize? You know that general case it is V1 minus V2 or V2 minus V1. So first thing I have to apply is that as the input I have to apply 2 numbers V1 and V2, and they should not be equal, because if they are equal the fault will not be sensitized, as simple as that. So basically I am applying, I have to first enable this scan. Why I have to enable this scan? Basically because if you see this V1 and V2 are going as a feedback from this to register back. So if I do not set this flip-flop as a scan mode, then actually I have to use the old circuitry, and I have to make some numbers at register A and some numbers have to go to register B, which should be not equal and so forth. So we did not go by that. We instead use the scan chain, and there will be, if the number is say 128 bit each, so this scan chain length is 128 into 2, and you feed the values into the scan, so that these two are two non-equal numbers. That is, maybe you are setting the value of 16 here, and maybe you are setting the value of 121 here. Two different values I put to these numbers, so that V1 and V2 is not equal. That I will do by scan. So initially scan chain will be enabled and I will do it. So basic concept actually always remains same. That is have to be fact. The scan chain will remain same. Sensitize, propagate and justify will remain same. Only thing is that we are going to higher level of abstraction. The basic remains same. Only the concept changes whenever we are going for abstraction level, but the basic philosophy of algorithms always remains same. So basics of computer science will never change basically. So what we are doing, we are enabling the scan. V1 is not equal to V2 for sensitizing it, and actually we have to make select, we are making select equal to 0. You can even make select 5 6 equal to 1, that also is possible, because if you are making select 5 6 equal to 0, then what happens basically, from here V2 is going to come, and from here again due to a swap, again the V2 is going to so basically what I am doing, I am making this select equal to say 0. So in this case it will be actually V2 minus V2 will be the sorry, this one, actually this is the swapped values. So if you look at it, this is the swapped values basically. So you are going to get the value of V2 minus V2. In fact this one V1 and V2 in the normal case, but now it is swapped, it is V2 and V1. So this was V1 V2, and by swapping it has become V2 V1. So you are going to get the value of V2 minus V2. In fact basically you could have also taken the value of select 5 6 equal to 1. In that case you would have got the value of V1 and V1 minus V1. So that is immaterial, you can take anything. Now one point, how do I make select 5 2 equal to 0 or 1 directly? In fact select 5 6 is fed by the controller, that is again a circuit. So again the controller circuit will also have scan chain, that is as I have shown you in the table, that is this table if you look at it. So this table is very easily implemented as a digital circuit from your undergraduate digital fundamentals. That circuit will also have flops. You can again set the scan flops, so that actually it will directly make the value of V5 6 equal to 0 or 1 as you like, right. So that is done. So now I have made it 5 6 from the control circuit by using again a scan business. So this is 0, and I am going to get the answer V2 minus V2 over here. Again you could have also made 5 6 equal to 1, then it will be V1 minus V2. Anyway, for the example I have taken this. So it is scan enabled. Let us again rub it and make it clear for you. So what I am having, scan is enabled. I am making V1 and V2 two different numbers of my choice, but they are not equal to. This is 0. So but basically the job is done. I am getting V2 minus V2. So the fault is sensitized. So here we are going to get the value 0, but in case of a normal circuit the value will be equal to non-zero, because V1 is not equal to V2. So now again let me zoom the relevant part of it. So the answer here is a D. That is normal case, the fault is 1. Should not, is actually D here is slightly different. It is non-zero versus 0. So in the normal case this value is non-zero, and the failure case the values are all zeros. But again I am telling you, it's not a single bit number, it's a bit width. So maybe V1 and V2 are 128 bit numbers. So this all the lines are actually 128 bits in nature. Here D means non-zero versus 0. Again I am selecting this line for the propagation, which I can easily do. It will be again D, the multiplexer will be D. So of course you have to make select 3 4 equal to 1, because I have to propagate this value, and I am just propagating the value through this. And basically, so scan is disabled, I am propagating the values from D, D and this is the selection path. And to justify what you have to do basically, similarly I am also showing the justification, or this is the propagation path. So justification here is very simple, you have to make 3 equal to 1, and basically you also have to make select equal to 1, and this can be x. So this is the propagation, and these two is very easily you can justify the value. So D will be latched over here. So in fact that is basically, you can say that this is your actually the justification values is, this is basically equal to 1, and select is equal to 1, and this is equal to x, not required. So basically if I say, make it clean, just propagation path, and basically these two are the justification path. Your job is done. Now D is latched over here. So what you do, so D is latched over here. Now you will be using a scan. Again you enable the scan and put the value at the output, and just check whether it is non-zero number or 0 number. If 0 number, this mask is having the problem of fault type else reverse, if else reverse, or it's a normal circuit. So concept is extremely similar, but basically instead of a considering all these numbers as a higher bit numbers, higher bit width, we are considering a single block, single line. So you can easily appreciate that even if the N1 and N2 are 128 bit, or whether they are 256 bit or 128 bit, the numbers will remain very, very limited to 11 blocks in this case. But if you are taking a gate level, it will actually blow up. So what we have achieved basically? So the number of RTL faults in this whole circuit, if you consider, is something around 19. Now I have also synthesized the circuit, then the number of stacked faults, and I have simply considered the inputs and outputs as only 8-bit numbers. In and into are only 8-bit numbers. Then the number of stacked faults is 844 around, including fault collapsing, etc. So you can see that the jump is so high. And if I consider the number from 8 bits to 128 bits, the number of faults will be something around 10 lakhs or 20 lakhs. But the RTL faults will never change, it will be always 19 in nature. And it is not only about this marks faults, I have taken all the relevant fault models for the multiplexers, subtractors, registers, less than equal to, greater than equal to, all the existing fault models which comes from the RTL fault model, like some which I have already discussed now, are all considered in all the blocks basically. Then the number of faults is 90, and here the number of faults, if you are synthesizing the whole circuit in terms of gates for 8-bit inputs, is 844. So you can easily see that I am going to lower the test pattern generation time like anything. So, and that is the thing you have to go if you are going for a NOC and SOC kind of a circuit. There is no other way other than going for abstraction. Another very important point is basically low number of test patterns. Because you have 19 faults, the number of test patterns will be 19 or even less than that. But if there are more number of faults, of course the number of test patterns will be higher. As I told you, always telling you that there are two types of complexity. One is test generation time, that is not of primary importance, but more important is how many test patterns you are applying, because that has to apply to all the circuits. So here with the lower number of RTL faults, the number of test patterns also comes down, so testing of each circuit will also come down. So that is what is a big achievement we have. So therefore, people are all moving towards RTL abstract level of testing in advanced circuits, because there is no other solution. But what we lose? Your accuracy may be lowered. People have till now, with all the fault models you are considering, people do not know that how many bridging faults are covered. Basically they are till now trying to mainly find the correlation with stacked faults, and slightly few works may be appearing which is for the bridging faults. But as of now, people mainly are looking at correlation between RTL and stack. Delay is no longer ensured by these methods, means they have no much studies on those areas. But people have still found out that there is good correlation between stack and RTL. And there is slightly quality compromise on the accuracy. But still, as you can appreciate, there is a huge jump in complexity. Like from my first lecture on testing, you might have found out that if I go for functional test, it is 2 to the power n. And if you go to structural test, it becomes 2n or even lower than that. So from complexity to very much linear kind of algorithm we are coming. But here also, if the number of n is also very large, the numbers of inputs, number of gates or nets are also very high, then again you have to even bring down the value of n. There is no other option other than to go for abstraction like RTL and RTL fault models. So even from 2n, we have got to something like n by maybe some tens of thousands or something like that we have brought down. If n is 10 lakhs, the number of an RTL, if you are going at the block level, it may be drastically brought down by the number of bit size, that may be 128 or 256, that is by the approximately by the bit width we are bringing down the number of nets or the gates. So the test pattern, number of test pattern, test time actually comes down. So basically this actually brings us to the end of the test methodologies for advanced circuits. So that what we have covered basically in this module, we have basically given you a very brief idea of testing, and then you have seen that for typically complex VLSI circuits, structural fault models like delay, bridging, etc. was still okay at the gate level. But when we are moving towards more advanced circuits like NOCs and SOCs, we have to consider the RTL or more abstracted view. And about the fault models, people are now moving from structural faults from stacked to bridging, delay and more sophisticated faults. Also we have discussed how optimization should be done at the level of the design for testable circuits, so that all the inbuilt circuits in the on-chip circuits for testing should be lower in number. Like how can you minimize the scan size, how can you optimize scan time, and how test pattern can be compressed. But these are all directions which are coming for advanced tests or advanced test concepts for modern circuits. So in fact, in this this course basically is a is not a very advanced course which gives you pointers towards the newer paradigms of testing. By no means like a classical CAD for VLSI can cover all the algorithms. But what I have tried to give, and I have tried to give you ideas that these are the open research avenues, what people are thinking, what people are trying to develop the test methods and fault models which will be applicable in the modern day concept. So, and we will upload many references in the website for which you can use to pursue research in the direction of testing. And in the next module, basically we will be looking at verification. In test, what we do, we take a circuit, give input, and we see whether it happens properly or not. So everything is based on the inputs we give. But can we mathematically guarantee that it will work for all conditions? It is not. Basically, it will actually make the problem very difficult, like an exhaustive testing. But still, for some cases, we require mathematical guarantee that whatever design you have done is mathematically proper. That is actually called formal verification. So formal verification is a more complicated problem than testing, because we have to guarantee entire correctness of the behavior. So in the next module, we will try to give how people have thought of optimizing the verification algorithms for very complex circuits. Thank you.